Welcome to the Connect with BMC Helix ITSM webinar series. During today's event, you're able to ask questions of our panelists. The questions and answers, along with this recording of this webinar, will be posted to our YouTube channel a week from today's date. Today's topic is leveraging AI/ML clustering for service desk processes. I'll turn it over to Harshad to take us through this content.
Thank you, Greg. My name is Harshad Borgaonkar, and I am a Principal Product Manager at BMC Software. And today I'll be joined by my colleague Ajoy Kumar, who is a lead R&D Solutions Architect. And in this webinar, we are going to take a look at our new AI capabilities within ITSM and how AI/ML clustering technologies are leveraged for effectively managing some of the service desk processes. In our agenda today, we'll go through an overview of what the new AI use cases are. We will then delve a bit deeper into both the AI use cases around proactive problem management and real-time incident correlation, along with short demos on both the use cases. We will then take a look at some of the clustering concepts and the AI/ML algorithms that have made this possible. We will also provide an overview of the architecture along with the AI technology stack, and finally, we will provide some useful references that you can follow up on. The new AI-based use cases that we will be discussing today are around proactive problem management and real-time incident correlation. Both these use cases are based on ticket clustering, which then internally works on AI capabilities around NLP and clustering algorithms, which we will see later. The idea is to basically boost IT user productivity with AI and machine learning and impact some of the business or IT outcomes. So, in proactive problem management, we are leveraging ML based clustering to identify similarities between historical tickets and clustering them so that problem investigations could then be launched and problems can be mapped against these tickets. These tickets generally indicate an underlying root cause, and creating problem investigations easily off the UI enables problem coordinators to hand over this to problem investigators who could then work on resolving those underlying root causes of the problem which led to the occurrence of the tickets in the first place. This helps in preventing these incidents from reoccurring in the future and thereby reducing the incidents in service desk. And in incident correlation, this ticket clustering works by correlating incidents in real time and clustering them so that detection of an emerging impactful situation becomes easier. This also helps with faster reaction to such emerging situations and eliminating any manual tasks associated with identifying and managing duplicate incidents. And before we take a deep dive into these use cases, I will talk more about the specific problem that we are trying to solve. This will require us to dig a bit deeper into two personas and their specific pain points. So I'll start with proactive problem management, and we will look into the typical day in the life of a problem coordinator. Now, we all know that one of the pain points for a problem coordinator is to identify the most valuable ticket clusters so that they can be looked at from a problem investigation perspective. And problem investigations, as we know, are a very costly process, and that is why they prioritize them very diligently so as to look at the most impactful set of recurring incidents, because again there are too many tickets and you cannot pick all the tickets to perform problem investigations. It's really impossible. So problem coordinators have to select these tickets manually, and again when done manually, This takes several days because part of the issue is also analyzing key information on the ticket which comes as free text. And the other part is where these tickets need to be grouped and then problem investigations need to be created. And both are tedious and time consuming activities, which is one reason why problems go unmitigated today. Now, we have applied a combination of NLP and AI clustering to solve this problem. These techniques, when combined together, help classify historical tickets into high value clusters and makes it easy for problem coordinators to target the most recurring ones. The way this works is that we build these ticket clusters by taking 6 months or 12 months or maybe even 2 years of ticket data and then run the algorithms through them in batch jobs, and this happens offline and it is typically a monthly process. The algorithms identify similarities in the ticket data and clusters them into groups which can be handed over to problem coordinators. Of course, this is around the AI engine part, but effective visualization and the ability to take actions of it is what really makes this work. So, when users actually see this intuitive dashboard displaying ticket clusters, it helps to know that there is an equally powerful AI engine at the back. At this point, I think it's a good segue to launch into the solution. So, what you are seeing over here are the dashboards, and as I mentioned earlier, this is the result of the outcome from the proactive problem management or PPM clustering jobs that run on the background. We can view them here in either the heat map or hotspot view or the more traditional list view as we will see later. Here in the heat map view, you can select what the size of these rectangles should represent, and then there are a couple of dimensions like number of incidents, total resolution time, total efforts by which you could do a size by on these rectangles, and then you can also select what the colors of the rectangles should represent, and they can be either average, priority, trend or service CI. You can observe the difference in the size and the color, and they all indicate something. But again, these parameters are customizable. And then in the list view, you've got a simple plain representation of facts that could be number of incidents, total resolution time, total efforts, average priority, and so forth. The benefit here is that you could sort the table in various ways like incident cluster name or number of incidents in a cluster or total efforts, and then see for yourself how much time an organization spends in solving these tickets. Ultimately, you could drill down from a cluster on the list view as well as from the heat map view to the list of incidents that make up for those clusters to investigate these clusters in detail. Now, you will also notice that there is a similar way to drill down from the clusters in the heat map view to the detailed cluster view as well. Now, this is also where you can create a problem investigation or relate an existing problem to an incident. If users want to do this directly through the heat map view, that is also possible because they can create a problem or relate an existing one through the kebab menu that appears on the top right of the cluster out here, and this enables them to create a problem or link it to an existing problem. The create problem option here takes the user to smart IT where the problem can be created and saved. Also, users can view the associated problems once they have been created in ITSM. Again, the value here is that users can take actions seamlessly while performing the analysis. Then there is the feature to limit the clusters in the heat map view to 50 with a default of 25. Also, users can select any number of clusters between 5 and 50 with a step size of 5. The default size is again configurable, and if users want to change that or modify that, they can also be able to do that. There is also an information bar that displays the selected number of clusters against the total number of clusters. And if there are a lot of clusters which are more than 50 and users want to view all the clusters, they can view them in the list view tab. Users can also download this information to a CSV file or a PDF file if they wish to perform any offline analysis. So, just to recap what we have seen here and understand the interplay of different roles, the problem coordinators are now able to automatically identify recurring incidents within the set of closed incidents using a dashboard that displays incident clusters and allows for additional analysis. Once they analyze these clusters of incidents, they can create problem investigations which are then transferred to more specialist teams of investigation of investigators such as SMEs who then work on the problem to resolve the root cause by creating either a change request or creating a workaround and a known error for this. The benefit of this use case is in terms of efficiency, simplification, and increasing productivity. So, on the one hand, we are now able to reduce the efforts for incident analysis and problem creation by running clustering jobs in the background to create the incident clusters and seamlessly launching into problems of the same UI. And on the other hand, this aids in an improved identification of your most valuable incident clusters, which ultimately supports reduction of incidents to your service desk. Lastly, there is better alignment around focus areas through data driven decisions and good visualizations. The second use case that we indicated is the real time incident correlation. And one of the major differences between this and the earlier use case is that, unlike proactive problem management that deals with historical tickets, incident correlation deals with real time incidents. So, think about real time incident correlation as a counterpart which is also based on ticket clustering but which deals with more real time incidents as they come into the service desk. So, you are clustering on the fly as incidents are coming to the service desk. You need to understand which of these incidents are about the same underlying issue or situation. This becomes critical as a flood of incidents could indicate an emerging impactful situation, such as a major incident. So, the persona here that we are talking about is that of a major incident manager. And if you look at how they detect emerging situations today, then this is largely through the word of mouth, where agents could look at a ticket console here or a dashboard there and make some suggestions. Overall, again, this is a very manual process, and what customers need really is an analytical process that helps them to identify these clusters of incoming incidents and understand what is currently going on in the service desk. So, a dashboard that shows emerging topics in real time would really facilitate a quick and coordinated response. Also, what is needed here is a way to formally relate these incidents and reduce any duplicate work so that incident management activities such as notifications could be streamlined. And lastly, you would need system guidance such as probable cause analysis to reduce time to resolution and restore the service as fast as possible. So, again, those are some of the requirements of a major incident manager to help them perform their jobs better. Now, coming to our solution and the use case. So, what we have done here is that we have leveraged AI based algorithms such as NLP and clustering to accurately identify incidents in real time that are related to the same underlying situation. What you see on the screen here is that we have an incident command center of sorts to understand these emerging incident topics in real time. And now that these incidents are clustered, we can also manage duplicates so that incident response teams understand the patterns and the duplicates that are associated with them. Finally, you can link an incident to a probable cause analysis in AI ops that enables for faster resolution of issues as users can explore the probable cause with a probability percentage, look at the nodes in the topology, and identify with some percentage of probability what is the likely cause. And again, at this point, it's a good segue to launch into the solution. So, what you see here in the real time incident correlation workspace is the dashboard or the billboard view of the incident clusters. By default, as you will notice, they are sorted by the number of incidents in each cluster, but you can change the sorting to average priority as well, in which those clusters that have higher priority incidents will be displayed first. And you can also notice that the billboard has been refreshed just now, so you are sure that you are viewing real-time incident clusters as they occur. Now, once you click on a cluster, you can see all the incidents that form that cluster. The default set of columns are shown in this detailed view. If users want to add additional columns, they can click on visible columns here and add more columns as they deem fit. Users can also manage duplicate incidents by relating them to a parent. This allows incident response teams to focus on the parent incident which needs to be resolved. There is this feature in the cluster detail view where users can view relationship between incidents. So, depending on whether the incident is a parent or a duplicate, the relationship column will either show duplicates or show parent. Clicking on show duplicates will open a modal window and users can see all the duplicate incidents that are associated with this parent. And of course, this is also dependent on users tagging an incident as original in Smart IT, which then becomes the parent incident. And the icon to the right of the incident number indicates that this incident is a parent incident. And finally, you can filter these incidents by incident numbers or summary or assignee or an assignee group and apply those filters in case you want to only view those selected incidents in the detailed cluster view. So let me recap what we have seen earlier and how various personas and teams have their roles to play. So what we have seen is that AI clustering jobs can automatically identify clusters of incoming incidents that could indicate an emerging impactful situation or a major incident. This impactful situation is visible on the dashboard for major incident managers and other personas to review the emerging incident clusters, and they can also relate individual incidents as duplicates to streamline the incident management activity. They can also take actions of the same UI without needing to navigate back to Smart IT and performing these actions. Finally, based on the information on the dashboard, they can determine if the underlying service is a critical one. The actions could also include leveraging the same dashboard to discuss with incident response team on the emerging situation and what the probable causes could be. And talking about the benefits, the current efforts on identifying duplicates are avoided because the AI clustering jobs can correlate incidents together, and the UI provides an easy option for marking duplicates. Again, getting real time information enables faster reaction time to emerging situations, and this helps in reducing downtimes of applications or services. This becomes very important when a service is very critical. Lastly, they can avoid multiple agents working on the same duplicate incidents in silos because the effort of identifying and detecting duplicates is now synchronized. Yes, and that concludes my portion. We'll hand it over to Ajoy.
Thank you, Harshad. I'm going to walk you through the two AI ML algorithms that drive proactive problem management and incident correlation. The proactive problem management is driven by k-means. We'll cover that in quite a bit of details. The incident correlation is driven by a real-time streaming algorithm. But before we jump into these algorithms, let's cover some of the basic concepts of clustering. The basic idea of clustering is to group incidents into something meaningful. What you see here is a green cluster of VPN password resets. It has 5 incidents, and all of them appear to be about a password reset issue. The sentences within each of those incidents need not be exact, but still each of them is really talking about a VPN password reset. The left one is another cluster. It's all about a connection failure issue. It can be, some of the incidents are on Skype, some are in VPN. Clustering is a unsupervised algorithm, so you don't require any training. Essentially, you feed in all the data, all these incidents, and it's going to look and compare all the incidents and figure out automatically the patterns and relationships among the text fields within all the incidents and try to group them on its own. That really saves a lot of time because there is no training overhead for both PPM and IC. We are going to cover the 3 algorithms: k-means, streaming clustering, and then topic modeling. Topic modeling is used to really identify a title for a set of incidents in a cluster. As you know, every AI algorithm requires a lot of hyperparameters to make it work correctly. You really need to guide it in a proper way so that you get the right clusters. These are 5 core hyperparameters that are available in the product. Let's begin one by one on what these are. The first one is the text field. This is a field used to specify which of the fields in an incident are you going to do clustering on. Typically, folks use description, summary field where there is a lot of free text typed up. That's what you use for text fields. It really defines how your clustering gets done. Of course, not all words in this field, in the text field, are important. So typically what happens is you want to remove some of the common words like a, the, in, ours. Those words don't really matter for when you do clustering. So we automatically remove stop words, but we also provide the flexibility so you can define your own stop words. For example, if you have a company name or a region which keeps appearing in every incident or in most of the incidents, you perhaps want to remove those so that clusters can be defined without those names biasing the clusters. So we talked about the two hyperparameters. The third one is a group by field. We'll talk about it in the next slide. It allows you to define how crisp your boundaries for each of the clusters would be. The fourth parameter is number of clusters. This is important parameter for proactive problem management, K-means algorithm. Typically, you use your domain knowledge or number of categorizations or how many problem investigations you typically do every month. That's a number which you can specify in the system. But if you don't know what that ideal number of clusters or number of potential problems need to be, you can always let AI algorithm pick it. So we also have a feature called optimal K, which will pick the right set of clusters for you. So you don't need to make a guess. And then finally, similarity threshold is also another hyperparameter used in incident correlation to compare how close two incidents are. Let's dive into group by field, which defines the boundaries of a cluster. If you look at this page, and you're going to see a lot of clusters which are mixed. Let's look at the left set of clusters. You have password reset cluster, which has Teams, VPN, Skype incidents. So you have a mixed cluster. Basically, what this means is that your boundaries of the clusters are not going to be defined within a business service or within a company. But if you look at the right, you could specify a group by field, such as by business service. And in this case, every cluster will be uniquely belong to a specific business service. For example, you have Teams business service, and within Teams, you have two clusters. One is a password reset, one is cannot call. But both these clusters are all about Teams incidents. So the same thing happens with Skype, VPN, and so on. So when organizations have tech stack ownership or application ownership, and you are heavily into service aware organizations, then it makes sense to use this. If you have different companies on how you manage your incidents, you could use that as a group by field. One of the power of the product is that you have a lot of capability and flexibility to fine tune all these parameters so you can get the right clusters. Let's look at data processing pipeline. As you know, all the ML algorithms require numeric values to work their algorithms. But most of the incidents which are typed by humans is all text. So the data processing pipeline takes text and converts it into a vector of numbers. That's what you see is going on here. You have text like I cannot connect to Skype. It goes through a series of steps like tokenization, stop word removal. We talked about that, where you have the flexibility to define your own stop words. It goes through stemming and lemmatization to convert words like ran, running, all into its core stem word like run. And then finally, it does vectorization. Vectorization, there are multiple techniques to it, such as TF-IDF, or BERT. BERT is one of a very powerful language model that Google recently came up with, and we use that to vectorize. We'll talk about it when we discuss incident correlation. The data processing pipeline is built into the product, and you have a few control knobs to fine-tune stop words. Now we'll talk about k-means. The best way to understand k-means is goes through the example. So let's begin. Each of the gray dots here on the diagram represents an incident. When k-means begins, it randomly picks 3 points. It chose 3 because that's the number of clusters the user has asked it to cluster. It picks 3 random points, and those are listed on the diagram here and indicated as blue, green, and yellow. Next, what it does is every gray incident is compared with each of these 3 points, and the incident belongs to one of them when that distance is the smallest. So you basically go through that, and now you have a set of yellow points which are closest to this yellow center. You have a set of blue closest to this blue center, and you have a green cluster. So now you have identified 3 clusters, but this is not really the best clusters you can get. So what it does is it goes through the second iteration where it figures out for each of these clusters, it finds the new centroid, or which is the center of the cluster. For green cluster, what is the center of blue? So what you see here is all these arrows are showing you that there are new centers identified based on your first round of clustering. Once you have identified these new centers for yellow, blue, and green, you go through the whole process again. You take every incident, compare it with the 3 new centers or 3 new centroids, and figure out where it belongs to. You're going to get slightly different clusters in this case. As you see, the yellow cluster grew a little bit because some of these incidents which were blue and green are really closest to this centroid. So that's how the clusters are dynamically forming. Now we have completed the second iteration, and you again go through the same process. Now that you have clusters after second round, you find the center for each of these clusters and go through iteratively until you hit a stopping condition. The stopping condition is when the centroids do not move at all, or if you have finished a set of fixed number of iterations. You can read about it in this web page. There are also a lot of research papers on k-means if you are interested. So what we saw here is the data processing pipeline of converting incident into a vector of numbers is very important, because once you have a series of numbers, then I can start measuring distance between incidents and centers as well as centroids, which is the mean of all the distances. Next, I'm going to talk about incident correlation. This is a streaming algorithm. The way it works is you start off with a few incidents, and as new incidents are created in real time, they get assigned to different clusters. Let's again take an example. So let's assume you just started your day and you have 2 incidents. You have backup fail, a green incident, and you have connect and issue, a blue incident. A second later, a new incident just shows up, which is this gray incident. The first thing it does is it vectorizes that gray incident into a set of numbers. That's where we use Google's BERT. And then it does a comparison of that vector with each of these 2. This one happened to be a backup failure incident, so it's going to match with backup fail, and that incident then becomes a part of backup fail cluster. So now you have seen that we started off with 2 incidents, but now we have 1 cluster of backup fail with 2 incidents, which has just formed. A few more incidents came in. you again go through the same process. You're comparing every incident with every other cluster or incident that exists. And in this case, what happened is one of them was a blue, one of them was a green incident, and now we have also a single incident VPN failing, which is just all by itself. Now, if you have been observing backup fail cluster, it grew from 2 to 3. So this is really showing you how the clusters can evolve over few minutes or over a few hours. This is an important concept, and this is all visualized in the demo that was shown to you sometime back, where the billboard view of real-time incident correlation continuously updates. And in this case, it's going to show you two clusters, a backup fail cluster and then a connect issue cluster. Another 4 incidents show up a few minutes later. They're all compared, and looks like all these 4 were VPN failing issue. So now you have a VPN fail cluster, which is the largest cluster, and that will show up at the top of your incident correlation screen. So the basic concept here is that the system is automatically doing iterative clustering as incidents are flowing into the system. And this allows you to detect major incidents very quickly. So it is almost like you get an early warning for a major incident. The core underlying technology we have used is DistilBERT, which is a very efficient type of BERT language model that Google open sourced some time ago. Now I'm going to talk about architecture. The architecture for both incident correlation and proactive problem management is based on of 2 components. You have the convert server piece at the top, which is where we have built ITSM Insights as an innovation studio application. So all the UI you see, like the proactive problem management UI, where you create jobs, the heat map which you have seen, as well as the UI for billboard view, drill downs, everything is all built inside Convert Server on the top of Innovation Suite. On the bottom you see is the ADE. That's where we have all the AI ML logic implemented as microservices. So everything you see inside ADE is a containerized microservices that can horizontally scale. Let's now dive into how proactive problem management works. Let me show you the core microservices for proactive problem management. All these 3 microservices support PPM use case, job manager, which also includes a scheduler, clustering job, which is the heart of running the PPM k-means algorithm, and then ticket service. I'll show you how a job will get run and how the data flow happens between Convert Server and ADE. So let's assume somebody in proactive problem management starts a job. The job goes to job manager. It's going to essentially go and spin off a clustering job container, which will call ticket service, another microservice, which will fetch the bulk incidents so that it can start doing k-means. Once it's finished doing the k-means, it is going to write all the clusters it has found to Elastic Store, which is through another set of microservices. So this is the basic flow of how a job is triggered from Convert Server, but the bulk of the machine learning microservices are running inside ADE. All the results of the clusters are also stored in ADE. So when you go back to proactive problem management and click on the heat map view, you're going to retrieve the clusters which were just produced by the clustering job from the Elastic Store. Now I'm going to talk about incident correlation. These are the yellow services on the left you see that support incident correlation. Incident correlation is different from proactive problem management in the fact that it is real time. So we have used the webhook capability of Converge Server to continuously flow incidents that are created in Converge Server in ITSM into ADE. So the first stream you see here is every incident, as soon as it's created in Converge Server, it gets sent to incident ingestion microservice inside ADE. It basically then sends it over to clustering service over Kafka. Clustering service is where all the real-time correlation happens. It compares the incident and then it matches that incident using BERT embedding, and it starts building all the clusters. Once it's built all the clusters and continuously updating all the clusters, it writes to Elastic Store. So as new incidents flow in, this is a continuous process. They go to incident ingestion, they go to clustering service, and it's continuously updating and evolving the clusters. Clusters can get formed and then they can also get closed as incidents are resolved. So this is the basic flow for incident correlation. Now you might have noticed the trend lines on the clusters in the UI. We also use metric services to support that. So we calculate metrics on number of critical incidents, total number of incidents per cluster, and all that data is stored in Victoria metrics. Let me talk about the data layer. Now that we have covered the primary microservices in Converge Server and inside ADE that support both the use cases. The data layer has 3 core databases. You have the Postgres database, where all the metadata, configuration data, all the hyperparameters that I talked about, all that configuration is stored over here. You have Elastic Store, which is where all the cluster results are stored. And then finally, you have Victoria metrics, where we store all the time series data like the metrics on the clusters. So this really completes the architecture slide. Of course, from a permission view, the row level security, everything happens in the ITSM or the Converge server layer, but the users are also synced between Converge server and ADE. So we do have a RBAC model which is followed end to end. Let's talk about what we saw today. Earlier today, Harshad talked about proactive problem management and incident correlation, the 2 new use cases that are powered by AI and ML. We covered the core clustering concepts, and we went into deep dives into AI ML algorithms for each of the 2 use cases. And then finally, we showed you the architecture in my previous slide. That really completes my talk. Let me hand it over to Greg now.
Thank you. And now I'll take us through the self-help in contacting BMC. The YouTube channel where this webinar will be posted is listed here. It contains past webinars as well as a rich set of how-to videos. The Connect with BMC Helix ITSM and Remedy webinar schedule is available at this community's link, and the hot off the press newsletter for trending information is available at this community's post. As always, contacting technical support via web, phone, email, and these social channels is available. At this time, that will conclude this webinar. Thank you for attending.